Okay, welcome back, folks, to regression analysis. In the previous lecture, we'll establish the essence of multiple regression and talk about how to estimate the parameters using OLS. And then we said because the computations can be difficult, there is a nice way of doing things, which is the matrix form of doing calculations or manipulations in multiple regression. So this is the slide we got to. We're trying to derive the OLS estimators by minimizing sum of squared residuals. Okay, so the problem is to minimize sum of the squared residuals. Remember, these are individuals UIs, okay, and this, pay attention, there's no summation sign here. This is a matrix, transpose matrix. I want to show you how this is equal to that, okay? If you take a matrix, transpose, multiply by the original matrix, of vectors in this case, is just the sum of the square of the individual terms. So please keep an eye on this. I'm going to do one example and that will be all. In the future, please remember that the transpose can translate into summation of the square of individual terms. Take, for example, remember our use of the form, let's say 1, 2, okay, and therefore U transpose will be something like 1, 2, and if I were to multiply U transpose U, then that is 1, 2 multiplying 1, 2. And what is it in matrix multiplication? You take this row, multiply this column, so it's going to be 1 times 1 plus 2 times 2, which is essentially what I want to show, right? 1 squared plus 2 squared, okay? So you see there's 1 here, it becomes 1 squared. There's 2 here, it becomes 2 squared. That's it. So a vector or matrix transpose itself in the case where we have an n by 1 matrix, it is just the sum of the square of the terms. Now like 1 squared, 2 squared, okay. So keep an eye on that. I will sometimes write this and later move it into summation of the individual terms. There are no i's here. It's the individual terms in the matrix or vector that have the i's. Okay, so this is the problem. Remember, y, big Y is what? X beta in a matrix form plus U. And therefore U is what? Y minus X beta. So this is U transpose U, or U prime U, as sometimes I will call it. So let's multiply out. This multiplied by that is Y transpose Y. And then I have this multiplying this. Okay, there's something you should remember from matrix transpose. AB transpose is what? B transpose, A transpose. That's what I'm going to apply here. So I'm having X beta transpose multiplied by Y. So this becomes beta transpose X transpose, then times the Y. Okay, take your time and then you will get it. Now, the next multiplication, this times that, but this Y must come with a transpose. So Y transpose is here, then X beta is here. Then finally, we are doing this. So this is beta transpose, X beta. So practice these things. Sometimes we ask for them in exams. You derive them once in your lifetime before you start using computers. Okay, so let's simplify this. This is just repeated here. This is also repeated here. These two were put together into one of them. Okay, these two, when you put them, it's just twice one of them. And I will show you why it is so. Okay, the idea is that if you are to multiply this out, it becomes a scalar, like a number. And this is also just the same number. And since they are the same matrices involved, beta, beta, x, x, y, y, they must be the same. Okay. Take, for example, this one. This is what? Beta transpose x transpose y. And this one is what? Y transpose x beta. Let's explore the dimensions. Okay, I'm going to do something like this. If you have a 2 by 2 matrix, you multiply by 2 by 1, then you expect the results to be 2 by 1. Okay, because the middle terms are the same. The resulting matrix will be 2 by 1. That's what I want to show, that the dimension of this will be equal to this, and therefore they are actually the same if they will just become a scalar. So remember, beta itself is p by 1. Okay, remember that we have y is n by 1, x is n by p. Go back to the previous lecture, you remember beta is what? P by 1, and u is n by 1. So I'm just going to be using their dimensions. Now, beta is p by 1, but because it's transpose, it becomes 1 by p. X is n by p. Because it's transpose, then it is p by n. P by n. And y is what? N by 1. So if you multiply this, the middle terms are the same. So the result from these two will be 1 by n. And this is just repeated here, n by 1. The middle terms are the same, so the result will be a 1 by 1 matrix. 1 by 1 just means it's a number, a scalar. Okay, let's explore this one too. Y transpose is 1 by n. What is x? N by p. And what is beta? P by 1. The middle terms are the same. So when you combine these two, you get 1 by p. And then I'll repeat this guy, p by 1. The middle terms are the same, so you get 1 by 1. That's the idea. If this will result in a scalar, just one number, this is also result in a single number scalar. And they are all beta xy. Beta xy, in a sense, is just a transpose, but they are the same numbers. Then they are the same. Therefore, we combine them to just be one of them. The one we choose to use here is because of foresight. We know what we are expecting. Okay. Therefore, we differentiate. The differentiation also comes from matrices. You may have to pick an example like I did before you can see, but I'll show you the next slide, the formula I applied from matrix algebra. If you differentiate this here with respect to beta, you get 2x transpose x beta. If you differentiated this with respect to beta, you get 2x transpose y. Okay, it works. I'm not going to go into details, but you will need to pick a matrix beta, transpose it, and then x transpose y, and differentiate with respect to beta. You will see that you get this. Okay, and now on the next slide, you will see, okay, let me go there and show you the algebra. So look at the algebra here, the matrix algebra. It says that if I have z equals to something transpose something y, and I'm differentiating this z with respect to the thing that has a transpose and is here, so that's with respect to y, then in other words, I'm differentiating this with respect to y. The result is what? Ay plus A transpose y. It works in matrix algebra. You may have to pick example to see that. But in particular, if A is symmetric, then this derivative is just twice ay. Okay? So if I'm differentiating something like this with respect to y, where y is the one sandwiching the a, and a is symmetric, y is here, its transpose is here, the result is just twice ay. Go back to what we did. So this is it here, right? Look at our y here, the y transpose, and the a here. A is symmetric, so it's just twice ay. Okay, think about it. Or you may have to pick examples and then you will see it. Okay. Now this one too follows from the other side. The 2 has just been repeated. But if you look at the next slide where I'm showing the matrix algebra, okay, this is probably not there, but let me see. It's probably not there, but it works, okay? This becomes twice S transpose Y, okay? Differentiating this respect to beta, you should be able to see that beta prime is not a problem. It is just transposing them. Think about it. If beta is beta 1 and beta 2, then beta transpose is just what? Beta 1, beta 2. I can differentiate with respect to beta 1 here and beta 2. Here too, I can differentiate with respect to beta 2. So the transpose here should not confuse that, oh, why are we differentiating with respect to beta? And this is actually beta prime. Within it, it works because the transpose is just rearranging them and the derivative goes through. Okay. So from here, you divide through by 2, cancel 2, transfer that one to the other side, and you have something like this. And we are looking for beta hat. So you pre-multiply both sides by x transpose x, and pre-multiply this also by, x transpose x inverse. That's the only way beta will stand free. And then x transpose x inverse is also used to multiply this. So these are beta hat. You must remember this. If you are asleep, they ask you what's the OLS estimate in multiple regression. In the matrix form is x transpose x inverse. You must always remember this when you're going to an exam, x transpose y. A matrix is symmetric if A transpose is the same as A. Remember that x transpose x is symmetric, right? If I were to transpose it, I'll get the same thing. It will be x transpose, and then the x transpose again. So it's x transpose x, so it's symmetric. So these are OLS estimator, and it exists as long as what? This inverse exists. So the matrix must be a matrix that has this matrix x transpose x must have an inverse, okay, a non-singular matrix. Those who did linear algebra, I think most of you, almost all of you did, you remember the idea of linearly independent. So none of the columns is a multiple of the other. In that case, we'll be able to find the inverse. So that's our estimator, okay? And this is also coming from some previous slides. If we were to manually multiply out, I think I showed you the first line. Okay, let's probably go back there. Look at this, keep an eye on this. There is n, sum of xi1, xi2, all the way to xik, and sum of y. I showed you before from that ugly looking maximization problem over here, right? That if you were to arrange them, this sigma y was the one at the tail end on the right. The n comes, the n is isolated, followed by what? xi1, xi2, sum of xi1, sum of xi2. The betas they were just collected elsewhere. Beta 0, beta 1, all the way to beta k. And then they took the coefficient like n, and then they took sum of xi1 and so on. So that's what is going on there. If you were to multiply this one, if you take this row and multiply by the betas, you will get the first equation on that slide I just moved away from. I think about it, n will now multiply beta 0 hat, this will now multiply that, and so on. So that's where it's coming from. This is useful in an exam or an exercise where they don't go all the way up to n. They don't go, this is what 1, 2, 3, all the way up to n. They can just restrict to a 3 by 3 matrix, and they will expect you to know that this first, the element here are the betas. The first element here is the sum of y's. This becomes sum of the first regressor and the y, and so on up to the end. So they expect you to remember this pattern and what is in here also. So learn them, be able to take a piece of paper and write out what is here, this whole thing, without blinking. It's doable, right? I know n is here, all of them have summation. I know the I means the individual, and the 1 is the first regressor, like education, experience, blah, 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 and so on. take your time, know the mechanics, it helps. Even in graduate school, it will be useful. Let's do some algebra here just to build your capacity with manipulation as we do in regression analysis. Okay, so how is it like okay, so what is our y? Y is x beta plus u. So what is y hat? Y hat is x beta hat. Remember, you don't have to add a u hat. As I said, once it's prediction, the best forecast of u hat is 0. So our y hat is x beta hat. So this is the x. This x here, this x has just been repeated here. And beta hat here has been repeated here because beta hat is x transpose x inverse x transpose y. So all together, we will call this thing here H. Okay, so it becomes HY. This is just showing some of the manipulation that go on, and then in exam they will tell you, show that this is equal to that. So to build capacity, how we manipulate things. This H here is called a hat matrix. It's an n by n matrix and called a hat matrix. So remember the hat matrix, how it looks like. You should be able to write it down without even looking. It's X transpose, X inverse, X transpose. Now, what is our residual? U hat is always Y minus Y hat. That is Y minus Y hat. Remember, this is Y hat. Okay, Y hat. So Y minus, but Y hat can be written as HY. So Y minus Y hat. And then you can factorize Y out. Once you factorize, because we are in matrices, you must, it's not the number 1 that will be left. It's the identity matrix, I minus H. Okay. So sometimes in exam, they can say, show that the residual can be written as Y, I minus H, where H is the hat matrix. You should be able to do the manipulations. Let's explore more of and show that our beta hat in the matrix form can be shown to be unbiased. So what is expectation of beta hat? That's expectation of X transpose X inverse X transpose Y. So what is our Y? Y is replaced by its expression here. And remember, X is non-stochastic. We assume X's are fixed. We can split this expansion into 2 parts. This part plus that part, take time. And expectation of all this is that the expectation will apply on the U. It goes to 0. And we'll be left with what? This part. Where's my eraser? So convince yourself why it is unbiased, right? This expectation will go to 0 because the expectation will operate on the U. We assume expectation of U is 0. Look at this. This and this will cancel. This whole thing will cancel this guy. So we'll be left with only beta. We have shown that it is what? It not when I say it cancel, I meant it to become the identity, right? So it's almost like just one kind of identity. So beta. So we've shown it's unbiased, right? Remember in the simple regression form, we found variance of beta 1 hat, variance of beta 1 hat in simple regression to be sigma squared sum of xi minus x bar all squared. Remember this. So equivalent, we want to see the variance of beta. Now we can't just write variance, it's covariance because this beta is a matrix, okay, or a vector. It has beta 1, beta 2, beta 3. Some people write variance, but that's fine. But think of it as covariance because the betas also have relationships. Okay. So remember covariance, right? In statistics, covariance of X and Y can be written as expectation of what? X minus expectation of X and then Y minus expectation of Y. So we are doing something like that, okay? So this time, the X and the Y, okay, appear to be the same. So let's say we have beta minus its expectation. This the big expectation is the one outside. So beta hat minus its expectation, and then beta hat minus its own expectation. But it's transpose, okay, because we are, it is matrix, okay? It is matrix. It's just like saying covariance of X and itself is just the variance of X, right? It's kind of related. So the idea of the covariance is what is applied here. It is in a matrix form, okay? It is in matrix form. So the idea is related to this, where we are having covariance of maybe X and itself. So I'm supposed to, so covariance of X and Y in statistics, you all know it is this. But I'm saying in our case, we are treating it like we are looking for variance of something, and it's the same as covariance of that thing and itself. So it is just like the X and the Y are the same. So you have to put X here and repeat it. But in matrices, you can't just write something and multiply by its own self. For matrix multiplication compatibility to hold, we always transpose one of them so that they'll be compatible. So it's a P by P symmetric matrix whose J diagonal is the variance of beta J, hat J, and whose ij of diagonal element is the covariance between beta. So you are going to see something like this, where we are saying that this will be variance of, let's say, beta 1 all the way the diagonal. This becomes variance of what? The last one, beta k. And then the terms in the middle, for example, this can be variance of beta 1, comma, beta 2. That's how this covariance matrix looks like. Okay, we'll probably have some examples at tutorials. So let's see, let's show covariance of beta hat. Okay, working further on that covariance of beta hat from here. Okay, we can also simplify it further on the next slide and show variance of beta. Covariance, which we could write as this, is also the same as what? This is beta hat X transpose X inverse X transpose Y. So remember the property I used before, right? Variance of a constant times a random variable W will be A squared variance of W, right? In statistics, this is easy to see. So here A is a constant, so treat the X's as a constant. So they are supposed to come out at squared and we'll be left with variance of Y. But you can't just take a matrix and square it, as I told you. So you put it here and put its transpose here. That's the idea of squaring the A squared. You can't just take this and square. These are matrices. They must be compatible in the multiplication. So you write, instead of square, write one here and write the other one and transpose it. Then they are sandwiching the variance of Y. Okay. We know variance of Y. We assume variance of Y here is sigma squared. So once we take this sigma squared away of, this is sigma squared, so it's a constant, so it can be factorized out. Then you can see that this, okay, this is multiplying this. Okay, let's try that. Let's try that and see how it turns out. So I'm saying this is a constant, it becomes sigma squared I. So you can kind of factorize it out. Okay, you can factor this out. I want to now show you the algebra when you multiply this and that. What is the final outcome? Remember, there is a transpose, so I'm going to operate it on this first and later operate it on this. Okay, and multiply with this. So I'll start by writing this out. It's X transpose X inverse X transpose. Now, when I operate this transpose on the element, remember AB transpose is what? B transpose, A transpose. So I'm going to operate this transpose on this. This is already transpose. When I operate this on it, then it becomes X. Now, X transpose X inverse is a symmetric matrix. So even if I transpose it, it remains the same thing. X transpose X inverse. Now, this thing here, it has its inverse here. So they both cancel and become the identity. So I'm left with X transpose X inverse. And my sigma squared was already factorized out. So this is the covariance matrix, how it looks like. So sometimes you can be given this matrix and sigma squared, and you should be able to tell that the diagonal elements are the variances of each beta, and then the IFJ's columns are the covariances as I showed on the previous slide. Okay, now let's explore for the purposes of hypothesis testing. Remember, we always want to have an estimate for sigma squared hat, and in the simple regression, until we ended up having something like UI hat squared over n, which we said is biased, and an unbiased form will be sigma sum of UI hat squared over n minus 2. Remember that, go back to the simple regression slide. So we said this was a better unbiased predictor of sigma squared. We always need this for hypothesis testing and or inference, okay? It was n minus 2. There is simple regression. There were two parameters, beta 0 and beta 1. So it would be the degree of freedom was n minus 2. Here that we have p parameters, that is k regressors having parameters plus 1. You expect that the denominator will be n minus p, but we'll get there. But first of all, let's show some of the derivations, how sum of squared error or residuals can have another representation. These are building your capacity, okay? When you go to graduate school, you can't just take regression without working through some of the matrices or what is going on. Okay, remember this thing here, y minus y hat, yi minus y hat is just ui, the residual, ui hat squared. So you know squaring the residual, the square of the residuals is just this, right? I've shown you already. It is just u, I've shown you this, is u transpose u, and this is just u transpose u. And we already showed you how to expand this bracket. We did it when we were deriving the OLS estimated. And I showed you how it simplifies to this. Remember that once you are using beta hat, they are the optimal OLS estimators. So we invoke this equality from a previous slide. Remember, this is how we solve for the betas and got beta hat to be x transpose x inverse x transpose y. This is our normal equations in matrix form. Let me go back there and show you here. So over here, we had it, right? At the optimum to derive beta, the least square normal equation. So this is what we are invoking. This equation is being invoked over there, okay? Because we are using the beta hat. So that, and that equation holds if only you have beta hat derived. So because of that, we are able to simplify this. This is just repeated, okay? And then we know that x transpose x beta hat, this part can be written as x transpose y. So this expression will becomes what? Beta hat transpose, and this part is the x transpose y. So it's very similar to this guy, and therefore when you add them, you get negative one of them. Okay. So sometimes they ask you to show that SSE, and you must not relax on this. Take a piece of paper and work them out yourself. Then you would have really enjoyed the regression class, and you would have learned a lot. So SSE can be written like this. Remember, x transpose x, y transpose y minus beta hat transpose x transpose y. Similarly, we can show the rest also look like this. Okay, this is what we just derived on the previous slide. So I'm going to show you how we come up with this. This I'm sure you've seen in your elementary statistics classes. Once we get this, we'll use the connection that SST is SS regression plus SSE, and then we can solve for this one. Okay. Okay, so let's continue. I want to show, remember our SST. Our SST is what? by definition, sum of y minus y bar squared. And you can always expand this, right, to be sum of y squared. All these are supposed to have i's, okay? Subscript i's, that's what I mean. Plus sum of y bar squared minus 2y y bar, okay? The summation runs through all of them. So this is just from secondary school factorization. Sorry, expansion of brackets. Okay. Oh, I keep missing the 2. Right, remember secondary school, you square that, and minus twice the sum of these. Okay, let me write this properly. I don't know why I'm missing the 2. So minus 2 summation of y bar. Okay, let's continue with the manipulation. So you have summation of y squared. Okay, and then when you sum, y bar is a mean itself, so it's a constant. Y bar is mean, and when you square it, it's a number, a constant. If you sum a constant n times, it will just end the same thing. Y bar squared, and then minus 2. Y bar is a constant, so I'm dragging it out of the summation sign, and I'm left with summation y. Okay, now I can easily write this as summation of y squared and then plus n y bar squared minus 2y bar. This sigma y, I want to convert it into y bar. Okay, so this sigma y, I want to convert it to y bar. So I divide through by n as we did before and cancel it here. Okay, so I can easily write this whole thing as summation y squared plus n y bar squared minus 2n y bar squared. Okay, because this becomes y bar, so y bar times y bar is y bar squared, there's n, there is 2. Okay, these are things you've seen before. Okay, so summation of yi squared. Okay, maybe right now, maybe let me make use of my i's, yi squared. Okay, so that you can see clearly what I'm trying to do. Okay, so remember these two would reduce, they are the same thing, so they are simplified. So this is, let's say, summation of, I'm supposed to have used I because this time I'm not really working with matrix. I'll switch to matrix very soon. Okay, maybe in the next 30 seconds or so. And this becomes my n y bar squared. Okay, I okay, so this is that. Okay, we already know summing. We can do a few more lines before I move to the matrix. So this is not matrix yet, it's still i's, individual i's minus, and what is y bar? Y bar squared is this actually, right? This thing here is y bar squared. This is y bar squared, right? This bracket here is y bar, so y bar squared. Okay, and then it's become sum of y I squared minus n over n squared sum of y I squared. Okay, so this becomes, I just took the n squared out of the bracket, so you have sum of y I squared minus sum of y I all squared over n. I'm sure you are familiar with this formula. You've seen it before somehow. Okay. Now we all know sigma yi squared can be written as what? The matrix one, y transpose y, right? This can easily be shown. I've shown you that it's become the sum of the individual items. And then we have minus summation of yi all squared over n. Beautiful. This is our SST. And we know that SSR is SST minus SSE. Excellent. Therefore, what is SSR? It's our SST. We just got SST here. Y transpose Y minus sum of yi squared over n. This is the SST. Then minus, what is SSE? We got it from the previous slide. And when we go back, maybe let me go back there and show you. It's here. This is what I derived that for you on the previous slide. And we got SSE to be like this. So this is what I'm going to subtract from there. Y transpose Y minus beta hat transpose X transpose Y. So minus what? Y transpose Y minus beta hat transpose X transpose Y. So this boils down to what? Y transpose Y cancels Y transpose Y. This becomes positive. So beta hat, do the algebra, you will see X transpose Y minus summation of yi squared over n. Okay, so that's what we have here. I've succeeded in proving all three for you. Okay, you see I'm a nice guy. I've shown you this right now. I had done this earlier and I'll show you the SST. Okay, you can be asked to show any of them on a test. So remember I told you that the MSC we did before was our sigma squared hat in a simple regression was the SSE over n minus 2, right? Because there were two parameters and here it becomes n minus p. Okay, SSE has been derived up here. SSE has been derived here. SSE, this is the one here. Okay. We'll talk about another concept, method of estimation, getting our parameters. It's important we describe the maximum likelihood, okay? Now, you know the least squares or the ordinary least squares, OLS. It's a way of estimating parameters. Now, I'm going to show you the maximum likelihood estimation also. As a star student, I'm sure you've heard maximum likelihood or you've met it before. So we are just maximizing the likelihood function to get estimated for our beta. We want to show that when you use maximum likelihood, OLS is just the same as beta hat MLE. Okay, so let's do that. Let me open, I'm going to open a new sheet, I beg your pardon, and then we derive these things. These two, you should know you could be asked to derive the MLE estimators. Earlier on, I showed you OLS estimators. I'm going to derive the MLE, maximum likelihood estimators. These estimators that are chosen and maximizes the likelihood, okay, of obtaining the data, okay, giving the values of the parameters. Okay. My plain sheet is here, my jotter. So we usually set up a likelihood function before we maximize it. So ML is just a way of estimating parameters, not just OLS. We have other ones, the method of moments. we are just showing you here the maximum likelihood estimators. Okay, so the PDF of the error term UI means an individual one. Okay, when we assume the errors are normally distributed, so you should be familiar with this by now. This PDF, okay, exponent or e to the power -1/2 sigma squared. Okay, I'm sure you are familiar with this thing. And then it will be UI. Okay, it's supposed to be UI minus its mean all squared, but the mean of UI is 0, right? So UI squared. I'm sure you are familiar with this PDF. So the likelihood function, okay, is the joint PDF. But the joint PDF is just a product of the marginals because we assume that the U's are independent. So the likelihood function is just a product up to n. This sign means product from I equals to n. Or we are multiplying the individual PDFs to get a joint PDF. We are multiplying because the marginals can be multiplied to get the joint if we assume independence. Okay, so I'm multiplying this PDF n times. So I have 1/sigma square root of 2 pi e to the power -1/2 sigma squared UI squared. This is the first one. Sorry, 1. This is the first one, so this will be 1. Then I multiply by the second term. Remember, I multiply n times. So 1/sigma 2 pi e to the power -1/2 sigma squared. This is the second one, so U2 squared. Then we multiply all the way to the nth one. So 1/sigma square root of 2 pi e to the power -1/2 sigma squared. Then we have U and the nth one squared. Excellent. Now we are going to use indices to simplify this. Indices. Look at this number, it's a constant. It's appearing here, appearing n times. It's appearing n times. So it just simplifies to 1/what? Sigma to the power n, the loss of indices. And then we have what? Square root of square root of square root of 2 pi, also raised to the power n because they are appearing n times. Okay, and then the e, loss of indices, the loss of indices. So you are going to add the powers. Okay, there's e power, they are all multiplying. So you pick one of the e and add the powers, right? If you have e to the power x, multiply e to the power y, then you have e to the power x plus y. So I'm just going to be adding the powers, e, add. So it's just -1/2 sigma squared u1 squared plus, but instead of plus, they are all having negatives. So it's proper to just use the negative 2 sigma squared u2 squared minus all the way to the last one, -1/2 sigma squared un squared. Okay, take your time, take a moment and check through this and check through. Okay, take a moment and check through. Okay, so I hope it is clear, the loss of indices that we have applied. Now, what I'm going to do is compress them further, algebra. Look at this. So I'm able to write this as what? 1/sigma power n 2 pi square root of that So let me take that again. Actually, I can write this as sigma n instead of the pi. Remember, the pi means power 1 over 2. So sorry, the square root means power 1 over 2. So I can write 2 pi. There's an n here, and the root means 1 over 2. Okay, so it becomes n over 2. And then I bring the e. All these, I'm factorizing them. I'm factorizing out. They all have this in common. They all have this in common. So when I factorize it, I'll be left with u1 squared plus u2 squared plus all the way un squared. So what do we have? I can go further and write it as what? Sigma negative n, right? Also the laws of indices. And then 2 pi raised to the power negative n over 2, and then e to the power negative 1 over 2 sigma squared, and condense that summation to ui squared. Okay, I'm summing all the ui's, all this ui plus this plus that is just a summation of that, or squared. Okay, remember this can also be written as what? Sigma negative n, and then I have 2 pi negative n over 2 e to the power minus 1 over 2 sigma squared. Now u transpose u, right? I'm summing individual u's, squaring them. Some I've shown you already. It's the same as u transpose u. Remember this. If not, go back to the beginning of the video. Of course, the u transpose u can be replaced with what the u's actually are. So sigma negative n 2 pi negative n over 2. Okay, and then e to the power negative 1 over 2 sigma squared u transpose u. Okay, so that's our L. Now we want to differentiate with respect to beta. Okay, we want to differentiate with respect to beta. Okay, usually this looks ugly. So when you take the natural log ln of L, it looks better to work with. So the loss of logarithm, if I took ln of this, it becomes negative n ln of sigma, the loss of logarithm. These are products, so I have to use plus, and this has negative already. So it becomes negative. Take your time. This is just the loss of logarithm. You have done core mass and elective mass. So this ln of 2 pi, the loss of logarithm, then minus 1 over 2 sigma squared y minus x beta transpose y minus x beta. Remember the e and the log, when they meet, they cancel, so I'm left with this. We are trying to get maximum likelihood estimator for beta. Now there's a little twist here. We want to maximize this log likelihood function. Look, this is a constant, this is a constant, and we are subtracting this from it. Think about this whole thing being your salary, and they are subtracting a tax. So your salary becomes maximum if what they are deducting is minimum. Okay, your salary becomes the biggest if the subtractions from your salary is minimum. So maximizing the log likelihood function to get the maximum, the beta hat maximum likelihood estimators, is equivalent to minimizing what we are subtracting. I'll take that again. I said if this whole thing is your salary becomes the highest if what they are subtracting, a deduction, is minimum. Because we are deducting this from the whole expression, the entire expression is maximum if what we are deducting is the minimum possible. In other words, maximizing this for the betas is same as minimizing this part, okay, minus 1 over 2 sigma squared y minus x beta transpose y minus x beta. In fact, this is a constant, so you can also throw it away, which means it's equivalent to minimizing y minus x beta transpose y minus x beta. Do you see something? Once we minimize this, we are able to get the MLE of this, the maximum for this. So when we go back to our slides, remember we have minimized this. Where is it? We have minimized this. When we're looking for OLS, we minimize the same thing. When we're looking for OLS, we minimize the same thing. And we're exploring the MLE too. We've gotten to a point where getting our MLE estimators implies just minimize the same thing. So we conclude that beta hat MLE will be the same as beta hat OLS as long as errors UIs are normally distributed. Remember, we use the normal distribution to derive it. Are normally distributed. As long as they are normally distributed. So remember this, beta hat OLS is the same as beta hat MLE. We don't need to continue further because we've already done it. Otherwise, I can copy the derivation, then come and paste here because we just have to minimize this as we've done before. Takeaway point, beta hat MLE is the same as beta hat OLS, only if we assume the errors are normally distributed. Okay, excellent. Now, next page, we will need this expression here. Okay, remember the likelihood function, we can write as what they use, errors, betas, and sigma. So let me open a new sheet. While we had an unbiased estimator, okay, for this to be SSE over n minus p, or U transpose U over n minus p, or y minus x beta transpose y minus x beta. We want to see the MLE estimate, okay, estimator for this thing, okay. Okay, when we're doing the OLS or using some mathematical statistics ideas, we have that once there are P parameters, the degree of freedom is n minus P. And in a simple regression, there were 2 parameters, so n minus P, or n minus 2 was what we used. Okay, let's see the MLE estimator for this sigma, okay, sigma squared. Recall that our log likelihood from the previous page is what? Negative n ln of sigma minus n over 2 ln of 2 pi minus 1 over 2 sigma squared y minus x beta y minus x beta. Okay, so let's differentiate with respect to sigma. The ln, the ln, let me get my eraser. We want an estimator for sigma squared. the ln of L over the sigma. Please, during exam, do not differentiate by sigma squared. It's by sigma. Okay, although we want estimator for sigma squared, the mathematics works, so it's just a clever way of going about it. Now, this in logarithm, okay, if you differentiate ln of x, what do you get? 1 over x. So if I differentiate this with respect to sigma, I get what? 1 over sigma. 1 over sigma. 1 over sigma. But there's n here. So instead of writing 1, let me just put the n. Okay, this one has no sigma, so you differentiate, it goes to 0. And this becomes what? Plus 1 over sigma cube y minus x beta transpose y minus x beta. How come the derivative of this becomes that? We have what? 1 over 2 sigma squared, which I can easily write as what? Oh, sorry, squared here. I can easily write as negative 1 over 2 sigma negative 2. Right? Laws of indices. So when you differentiate this, the negative 2 will cancel this negative half. So the negatives vanish, it becomes plus. Then you subtract 1 from the power, it becomes negative 3. And this is the same as 1 over sigma cube. Because I've differentiated, I'm looking for sigma, I have to set this to 0. Now you are back to commas. Look for sigma squared. So let's multiply through by sigma. It becomes negative n plus 1 over, okay, this was power 3, it becomes power 2 because I'm multiplying through by sigma. Then I have y minus x beta transpose y minus x beta equals to 0. We cross multiply by sigma squared. We have n sigma squared plus y minus x beta transpose. This is commas y minus oops, y minus x beta equals to 0. So we can solve for sigma squared hat to be what? Y minus x beta transpose y minus x beta all over n. So the MLE estimator for sigma squared is also biased, because if it were unbiased, it would have had minus p, okay, but it is consistent. So that ends the derivation there, okay. Let me go back to the slides. Okay, so we're trying to derive something. Where's my pen, pencil? Okay, we're trying to, where were we here before we went there? Okay, we passed all these places. Okay, so this MLE, we've succeeded in getting them. Let's discuss some properties of the MLE estimator, okay? And then I'll pause here and do a new video. In general, maximum likelihood estimators have better statistical properties than least square estimators. Actually, we assume normal distribution, right? We use the normal PDF. In MLE, once the distribution is correct, then it becomes better, okay? But if you mess up, it wasn't normal and you use normal, then you have messed up. That's the downside. You must get the full distribution assumptions correct. Okay, that's a disadvantage. But if you do, then we say that it has better statistical properties. Maximum likelihood estimators are unbiased and have minimum variance, okay? Maximum likelihood estimators are unbiased and have minimum variance. So the beta hat we got there are also unbiased and have minimum variance, okay? But the estimator of sigma squared over there was biased, okay? Now, they are also consistent, okay? This was biased, but because it was divided by over n, asymptotically it will be consistent, okay? And they are sufficient statistic, okay? Statistics is sufficient if no other statistic can be calculated using that same sample that gives new or additional information, okay? If a statistic is sufficient, and it was calculated from a sample. Then any other statistics you can calculate using that same sample, they wouldn't improve upon that estimator. Okay, so that's a sufficient statistic. Okay, so this is a disadvantage. While least square estimators require only second moment. Remember, in least square, we assume the errors have mean, zero, constant variance, and random errors. In maximum, like you need a full distribution assumption, like I said, whether it's normal distribution or Poisson or whatever, you must get that distribution right. Otherwise, so these things can be on the exam. They want you to know how MLE could be better than OLS estimators. Okay, so once again, MLE estimators are unbiased and have minimum variance. Okay, the blue we said are the OLS. It was true for only linear estimators, but MLE is superior even in the class of non-linear estimators, okay, and have minimum variance. Okay, so I will stop here and do another video. Okay, thank you. I hope you're enjoying the class. See you in another lecture. Okay, the part 3 of this second lecture. Bye.